Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. In 1989, I was in the news for inventing how to solve the toughest problems that arise in calculus, algebra, and physics, and for inventing how to solve those initial boundary value problems of modern calculus, and for inventing how to solve them across a new internet that is a new supercomputer and a new computer. The modern calculus is a tool that enables the mind to go where the eyes cannot see. Today, no extreme scale computational mathematician can live up to his or her name and do so without an intimate understanding of how and why the massively parallel processing supercomputer must be harnessed and used to solve the toughest problems arising in mathematics. I, Philip Emeagwali, was the headline stories of major U.S. newspapers, such as the June 20, 1990 issue of the Wall Street Journal. I was in the news because I invented how to solve the toughest problems arising in modern calculus. I was in the news because I discovered that the massively parallel processing supercomputer is de facto a new internet and a new computer that computes in parallel instead of the old computer that computed in sequence. Please allow me to quote from a book titled History of the Internet. Quote, in 1989, mathematician Philip Emeagwali shocked the supercomputer industry by performing the world's fastest computation, 3.1 billion calculations per second, using the power of internet. The results, as computer scientist Marshall Lakes put it, were phenomenal, 3 times faster than a supercomputer, unquote. On the 4th of July, 1989, I invented the precursor to the modern supercomputer, namely the massively parallel processing supercomputer. That new supercomputer that I invented became a tool that opened the door for an array of discoveries made across the sciences. Back in 1989, the full-scale supercomputer that I invented was powered by 65,536 tightly coupled processors that were already available in the market that shared nothing between each other, that were identical to each other, and that were equal distances afar and apart from each other. My invention that occurred on the 4th of July 1989 inspired the development of the modern supercomputer that is used to solve the toughest problems arising in calculus, algebra, and physics. Today, the most powerful supercomputer in the world is powered by an ensemble of 10,649,600 processors. In a strict sense, massively parallel processing supercomputing is not physics or mathematics. Yet, the invention and the continuous reinventions of the supercomputer must be intimately tied to the solving of the toughest problems that arise in physics and mathematics. The reason is in part because it is the quest for the solution for the grand challenge problems of mathematical physics that inspire the necessity to invent faster and faster supercomputers. It's often said that necessity is the mother of invention. The initial boundary value problems of modern mathematics that inspired and necessitated my parallel processing quest for the precursor to the fastest supercomputer of today was a system of ill-conditioned, heterogeneous, and anisotropic partial differential equations of the modern calculus. Such equations arise in highest resolution, massively parallel processed petroleum reservoir simulation. Such parallel processed simulators are used to make discrete representations of the Nigerian oil fields in the Niger Delta region of Nigeria. Such larger, higher fidelity and parallel processed petroleum reservoir simulators are used in Nigeria to make engineering decisions on how to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas that were buried a mile deep in the Niger Delta region of southeastern Nigeria. The unfortunate reality in oil-producing nations, such as my country of birth, Nigeria, is that the crude oil and natural gas that are easy to discover and recover have been discovered and recovered. In West Africa, the first oil field was discovered in Oloibiri in the southeastern region of Nigeria and discovered in 1956. That first oil field in West Africa began production back in 1958. That first oil field in West Africa dried up 20 years later in 1978. The important lesson from the Oloibiri oil field and for the 20 oil-producing nations in Africa is that the recently discovered oil deposits in Malawi, Niger, Chad, Cameroon, Uganda, Ghana, and Liberia could dry up in 20 years. The most important option left for abandoned Nigerian oil fields, such as the Oloibiri oil field, is to employ enhanced oil recovery processes. Such processes are a mix of techniques and technologies that tap on the knowledge of the new calculus that I mathematically discovered and the new supercomputer that I experimentally discovered. It was at 8:15 in the morning of the 4th of July, 1989, in Los Alamos, New Mexico, United States, that I experimentally discovered the massively parallel processing supercomputer. I invented the precursor to the modern supercomputer when I computed at the never before recorded speed of 3.1 billion calculations per second. I mathematically discovered that processors that could only calculate at the slow speed of 47,303 floating point arithmetical operations per second can be integrated across a small internet that is an ensemble of 65,536 identical processors. That new internet that I invented was a new supercomputer and a new computer. The massively parallel processing supercomputer must be used to solve the toughest problems arising in mathematics and physics. The toughest problems in calculus include the excruciatingly detailed petroleum reservoir simulations and the global climate modeling within a multidisciplinary environment. Both are multi-scaled in space and time. An example of multi-scaled mathematical physics and parallel processed model is the global climate model that simultaneously has grid sizes of 500 meters that sees the structure of the cloud and 200-fold increase in grid sizes of 100,000 meters that cannot see the structure of the cloud. Being multi-scaled made global climate modeling very computation intensive. The larger, higher fidelity petroleum reservoir simulation that must be executed across a heterogeneous reservoir formation demands parallel processed supercomputing and demands high performance computing from micro to macro scales. The petroleum reservoir simulation is computation intensive because the permeability and porosity within a production oil field changes in space. The petroleum reservoir simulation is computation intensive because it is multi-physics and non-linear in time. In multi-physics modeling, physical and chemical effects must be accounted for. In multi-physics and three-phased crude oil, injected water, and natural gas petroleum reservoir simulations, volatilization, chemical reactions, poroelastic behavior, non-isothermal and fractured flows must be accounted for. My 9 mathematical contributions to the partial differential equations of the modern calculus of petroleum reservoir simulation was the cover story of the top publications in mathematics, such as the May 1990 issue of the Science News. The Science News is a bi-monthly news journal that describes new mathematics as written by research mathematicians and as written for research mathematicians. My 9 mathematical inventions were 9 coupled, nonlinear, time-dependent, and never before scribbled across a blackboard partial differential equations of modern calculus. My new coupled system of partial differential equations is a subset of a larger coupled system of complex mathematical equations that describe pressure, velocity, saturation, and other variables. Please allow me to introduce myself. My name is Philip Emeagwali, but as a teenager in Onitsha, Nigeria, my name was Calculus. My contribution to mathematics is this: I invented how to solve the toughest problems in calculus. The excruciatingly detailed general circulation model executed across the massively parallel processing supercomputer that is powered by up to 10,649,600 processors is the instrument that must be used to foresee how the Atlantic Ocean will respond to climatic changes. The initial boundary value problem of calculus that defines the mathematical core of the general circulation model is one of the toughest problems in calculus. On the 4th of July, 1989, I invented how to solve the toughest problem arising in calculus. And I mathematically discovered how to solve that initial boundary value problem and how to solve it across a new internet that is a new global network of 2 raised to power 16 or 65,536 tightly coupled processors that were already available in the market and that were identical to each other and that were equal distances afar and apart from each other. I experimentally discovered that using only one processor to run a general circulation model was like putting the wings of a jet aircraft upon an ocean liner. In 1946, the programmable computer could only add 5,000 numbers per second. On June 20, 1974, and 28 years after that first computer, I began programming the first computer that was referred to as the first supercomputer. That first supercomputer could execute 1 million instructions per second. That first supercomputer was the world's fastest computer when it was released back in December 1965. It was on that first supercomputer that I began my quest for how and why parallel processing makes computers faster and makes supercomputers fastest. And super, namely the Philip Emeagwali formula that President Bill Clinton described in his speech of August 26, 2000. Inventing how to harness 64 binary thousand tightly coupled processors and how to harness them to solve the toughest problems arising in calculus, algebra, and physics is an endurance intellectual sport that took me 16 years onward of June 20, 1974 in Corvallis, Oregon, United States. That abstract mathematical and high-performance supercomputing quest required both discipline and concentration My invention of the massively parallel processing supercomputer that arose from that scientific quest entered into the June 20, 1990 issue of the Wall Street Journal. My invention of that precursor to the modern supercomputer was the cover story of many publications read by the physics, mathematics, and computing community. However, I did not become cover stories because of what I know. In scientific research, cover stories are about what we previously don't know, not what we know. The computer science teacher can only teach the computer we know. I conducted my scientific research to know what is discoverable and knowable, but which nobody knows. The grand challenge question of the massively parallel processing supercomputer that occupies the space of a soccer field and costs the budget of a small nation is so big. The question took me the decade and a half onward of June 20, 1974 to conceive that question, to ask that question, and to answer that question. In June 1970, and 5 months after the Nigerian Civil War had ended, I enrolled in Christ the King College, Onitsha, Nigeria. I enrolled for a year and a half. I enrolled for the 8th and 9th grades. I enrolled as Philip Emeagwali. Yet at alumni reunions, the old boys of Christ the King College of the early 1970s complained that they did not remember any student named Philip Emeagwali. However, the old boys of Christ the King College all remembered a maths whiz named Calculus. Philip Emeagwali is the actual name of Calculus. I was called Calculus because I spent most of my classroom time solving calculus problems. I solved the problems from the 568-page blue hardbound book that was titled, quote, An Introduction to the Infinitesimal Calculus, unquote. That calculus textbook was subtitled with applications to mechanics and physics. That calculus textbook was written by G.W. George William Count. That calculus textbook was published by Oxford University Press. For the next 20 years, I studied, conducted research, and invented new equations at the farthest frontier of the partial differential equations of the modern calculus. And I conducted research and I invented a new supercomputer. And I invented that new computer at the farthest frontier of the fastest supercomputers in the world. And I conducted research and invented how to push the frontiers of physics and do so at the crossroads where the most large-scaled computational fluid dynamics codes and the most massively parallel processed supercomputing met. During the 20 years onward of June 1970, I continuously conducted research and made discoveries and inventions at the boundaries of human knowledge in the fields of physics, calculus, and supercomputing. Fast forward 20 years, from June 1970 in Onitsha, Nigeria, The Nigerian Biafran Civil War that began on July 6, 1967 had just ended. That Biafran War ended 5 months earlier and on January 15, 1970. That Biafran War lasted 30 months, during which 1 in 50 million Biafrans died. During that civil war between Nigeria and Biafra, I was a 12-year-old to a 14-year-old refugee. My family lived in refugee camps in the 7 Biafran cities of Onitsha, Ogidi, Awka, Oba, Nnewi, Oketiti, and Ndoni. In June 1969, my family left the refugee camp at the formerly St. Joseph's Primary School, Oketiti, Biafra. We left Oketiti to become refugees in a small fishing village called Ndoni. Ndoni was along the banks of the River Niger. In July 1969, I was conscripted at gunpoint at the marketplace at Ndoni and conscripted to become a 14-year-old soldier in the Biafran army. I was sent directly and without military training to the Oguta war front. Oguta was at the west bank of Oguta Lake. Oguta was a 20-hour non-stop walk through swampy, knee-deep mosquito and alligator-infested waters. The mosquitoes buzzed louder in my ears than a jet fighter. I was more likely to be ambushed by alligators than ambushed by Nigerian soldiers. From Oguta war front, I was transferred back to the Biafran army at Ndoni. At Ndoni, I became a cook in the officers' mess of the Biafran army. Our small Biafran unit protected the small fishing village of Ndoni that was by the bank of the River Niger. In the early 1970s, I began to teach myself calculus. I did so while in the 8th grade of Christ the King College, Onitsha, East Central State, Nigeria. I taught myself calculus, and I did so from the 568-paged blue hardbound book that was published in 1914 and published by Oxford University Press. That calculus book was state of the art in 1914. That calculus book was rigorously written by a research mathematician for research mathematicians. That calculus book was also written for students of engineering and for pure mathematicians. That calculus book was written for the blackboard and not for the motherboard. The programmable supercomputer was invented in 1946, or 32 years after that calculus book was published. That calculus book had a closing chapter on the ordinary differential equation that is defined as an equality involving a function and its derivatives. And the ordinary differential equation was at the mathematical core of the grand challenge question that inspired the development of the first computer that is programmable and that computed automatically. That calculus book was not written for an 8th grader like myself in 1970, then at the Christ the King College, Onitsha, East Central State, Nigeria. In the mid-1970s, I studied the ordinary differential equations of calculus, and I studied those equations in Corvallis, Oregon, United States. The reason I evolved from a pure mathematician to a computational mathematician was because the ordinary differential equations that matter the most must be solved on a digital computer. In the late 1970s, I studied the partial differential equations of the modern calculus, and I studied those equations as an urban mathematician in the nation's capital of Washington, District of Columbia, United States. The reason I evolved from a sequential processing supercomputer scientist to a massively parallel processing supercomputer scientist was because the partial differential equations that matter the most must be solved on the fastest supercomputers that can be made. In the 1970s and 80s, the leaders of thought in the field of supercomputing ridiculed parallel processing as a beautiful theory that lacked experimental confirmation. So, in the 1970s, my mathematical grand challenge was to experimentally confirm that I could discretize the partial differential equations of the modern calculus and that I could solve the arising system of equations of extreme scale algebra that approximated those partial differential equations and solve those algebraic systems in parallel. That is, I solved them by first reformulating those partial differential equations and reformulating them as extreme scaled systems of equations of algebra, and second, solving those algebraic equations and solving them in parallel instead of solving them sequentially. Put differently, my mathematical quest was to both theoretically and experimentally discover how to parallel process by parallel computing across an as yet to exist primordial internet. I invented that new internet as a new global network of 2 raised to power 16 or 64 binary thousand tightly coupled already available processors that were identical to each other. I invented that new internet as a new global network of 65,536 identical tiny computers. Calculus gives us extraordinary power over the universe. Calculus makes it possible to forecast tomorrow's weather. Calculus is at the heart of the Industrial Revolution. In the 1980s, my scientific quest was for new calculus. I invented new calculus that I used to understand how to massively parallel process and how to communicate across my new internet. I invented that new internet as a new global network of 64 binary thousand tightly coupled already available processors, or as a new global network of as many identical computers that are equal distances afar and apart from each other. My lone wolf technological quest for the massively parallel processing supercomputer occurred across U.S. cities like College Park, Maryland, Fort Collins, Colorado, Laramie, Wyoming, and Chicago, Illinois. In the decades of the 1970s and 80s, I attended 500 weekly research seminars that each had the partial differential equation of modern calculus as a common denominator. Most of those research seminars were on progress made in modern algebra, modern calculus, and modern supercomputers. Each research seminar lecture was delivered by a research mathematician. Each research mathematician was visiting us from faraway places like Moscow, Russia, or Paris, France, or London, England. Each visiting research mathematician was invited to speak in the United States because he was at the frontier of knowledge in the mathematical and computational sciences. Each research mathematician presented to our local group of research mathematicians his mathematical discoveries from his quest for new mathematics. In the 1980s, I learned important lessons on how to create new mathematics. I learned those lessons from listening to the struggles of those 500 research mathematicians that attempted to, or failed, or succeeded in creating new mathematics. I learned how to discover partial differential equations that could be used to discover and recover otherwise undiscoverable and unrecoverable crude oil and natural gas that were buried a mile deep in the Niger Delta oil fields of the southeastern region of Nigeria. I learned how to invent partial differential equations that are yet to enter into the calculus textbook. To be exact, the visiting research mathematicians were demanded to state their exact contributions to the mathematical sciences and, where possible, their measurable contributions to extreme-scale computational mathematics. The genius is the ordinary person that found the extraordinary in the ordinary. The mathematical genius is the ordinary mathematician that discovered the extraordinary equation in the ordinary blackboard. It's one thing to have exclusive control of an ensemble of 65,536 processors. It's another thing to visualize those ensemble of processors as a new internet and to envision routing emails across 1,448,576 bidirectional, regular, and short email wires that were equal distances afar and apart from each other. I invented how to use those 1 binary million email wires to electronically marry those processors that shared nothing between each other, and to marry them together and marry them as one seamless, cohesive, never before seen supercomputer. My supercomputer invention made the news headlines in 1989 and thereafter. On the 4th of July 1989, I invented how to marry those processors as one seamless, cohesive, massively parallel processing supercomputer that is a new internet and a new computer. The modern supercomputer is like a wristwatch. You only see the face and the hands of a wristwatch. But the unseen inside of the wristwatch is abstract but necessary. My unseen 65,536 processors were like the inside of the wristwatch that is abstract but necessary. My 65,536 tightly coupled processors didn't solve the grand challenge problem of physics and didn't solve it by themselves. I used those 1 binary million or 1,048,576 regular, short, equidistant, and bidirectional email wires, and I used them to deliver my 64 binary thousand or 65,536 grand challenge problems to my as many processors and to deliver their companion instructions on how to solve those problems and to deliver the problems with a one-to-one correspondence to all my 65,536 processors that shared nothing between each other. Those processors were my set of laboratory instruments that made it possible for me to experimentally discover how and why parallel processing makes computers faster and makes supercomputers fastest and super, namely the Philip Emeagwali formula that then United States President Bill Clinton reconfirmed in his White House speech of August 26, 2000. My contributions to the development of the modern supercomputer include the following discoveries and inventions. I invented how to correctly encode the laws of physics into partial differential equations of calculus. I invented how to accurately discretize those partial differential equations into systems of equations of the most extreme scaled algebra. I invented how to code and solve those systems of equations across a new internet that I invented as a new global network of 65,536 tightly coupled, commonly available processors that shared nothing between each other. My contribution changed the way we look at the supercomputer that should become the computer of tomorrow. Making a technological invention demands an intercourse between the sciences and demands the exchange of fluids, or rather, the exchange of knowledge. That exchange is a necessary condition to making the scientific discovery. Scientific babies or new discoveries come from a respectful and joyous exchange of fluids. For me, Philip Emeagwali, that exchange of new knowledge occurred at the crossroad where physics, mathematics, and computers and computer science met, and occurred at 8:15 in the morning of the 4th of July, 1989, and occurred in Los Alamos, New Mexico, United States. That crossroad was where I invented the massively parallel processing supercomputer, and where I made the experimental discovery that opened new possibilities in supercomputing. I was in major US newspapers because I contributed to the development of the massively parallel processing supercomputer that processes across processors. I won the top accolades in supercomputing because I experimentally discovered how and why parallel processing makes computers faster and makes supercomputers fastest, namely the Philip Emeagwali formula that then US President Bill Clinton reconfirmed in his White House speech of August 26, 2000. Thank you very much. Philip Emeagwali. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.